Good morning. In the last module, we were discussing the boiling curve and its salient features. Today, in this module, we will complete the boiling curve discussion and proceed with certain terminologies that are there in the boiling curve. Boiling curve, as we said, was a representation or graphical representation of the heat flux versus wall superheat, and we did a thought experiment where we said that you could have a heater which could be a wire in a pool of water, and you have two types of experiment. One is the heat flux controlled experiment, the other is the wall temperature controlled experiment. We were doing the heat flux controlled experiment. By that I mean, heat flux control would mean that you are able to control the heat flux and allow it to remain constant for a given amount of time, increase the heat flux to a new value after that, and then proceed in this manner. So, heat flux controlled and wall temperature control, these are the two types of experiments that are done to generate the boiling curve. And as we said, boiling curve is a graphical representation of wall heat flux on the y axis. X axis is delta T, that is T wall minus T sat. You might also see some boiling curves with T wall alone as the x axis, does not matter, it is just a difference with a quantity which is T sat, which is a function of the local pressure. So, whether it is T wall or T wall minus T sat, the nature of the curve is not going to be different. What we are seeing is what we call as the pool boiling curve, and we said that pool boiling curve is easier to study because there is no effect of the force convection aspect, where the flow is going to also contribute to the increase in the heat transfer coefficient. And we did this thought experiment where we had a pool and we could either heat it this way, the way we did for making tea, or we could have a pool where the heater was in the form of a wire and there was water or whatever liquid at a local pressure here. So, heat is going to come either this way or this way, whatever be the nature of heating, the boiling curve would be the same. What you are going to see is going to be slightly different in these two cases. In the case of the first one, where you are supplying heat from the bottom, say by means of a gas stove or something like that, you will encounter the following regimes: Q double prime versus delta T. We said this is single phase natural convection, followed by what we call as nucleate boiling. We would start off with partial nucleate boiling and then go to saturated nucleate boiling, where partial nucleate boiling would represent growth of bubbles from the surface, maybe leaving the surface or leaving the surface and collapsing after a certain distance into the pool. When several bubbles are formed at the same time and they migrate to the surface, what you see is typically nice saturated nucleate boiling. This is what is very good about boiling, because with a small change in the heat flux, and small change in the wall temperature, you can achieve this amount of heat removal. And that is why the slope of this curve is almost in the log-log scale. This is a log-log plot. The slope of this curve is such that the index or the heat transfer coefficient is quite high. Now, if I do this thought experiment for a long time, for example, you keep the water for boiling when you are making tea and you are on the phone and you forget about it. What happens? After a certain amount of time, you reach a situation, maybe an hour or so, depending on the amount of inventory, that is the liquid, and the amount of heat that you are putting. So, integral Q double prime, this is watt per meter squared, area of the heater surface, times dt, integral 0 to t, is going to be your total heat. This is your wattage. So, if I go on heating for a particular amount of time, there would come a situation where all the water from this pool is evaporated. What you see probably would be, if I take this top view of this surface, what you would see is little bit of liquid here and there which is going to be there, or a uniform pool which is going to be there, and these would be dry patches, these would be liquid. Or progressively you might see liquid completely going out of the surface throughout. This situation where you don't have liquid in contact with the heated surface and you still continue heating. So, you are still on the phone and you have forgotten that you have kept water for boiling and you continue heating. What happens? There is no sink for the heat to go away. So, as you increase the Q, wall temperature will start to rise because the liquid is absent to remove the heat, and therefore what you would see is an excursion, very high rise in wall temperature. And this point where this transition from nucleate boiling to the sudden rise in wall temperature happens is conventionally referred to as the critical heat flux. This is a misnomer. By misnomer I mean this is not the correct terminology in terms of what actually it is. See, critical heat flux, that means it's so called maximum heat flux or something like that, but here it is not, it has nothing to do with the maximum. This situation could have happened at a lower heat flux with a greater amount of time. So, if the gas was on a medium flame and you were talking on the phone for 2 hours versus if the gas was on high flame and talking for 1 hour, you could get the same effect. So, the heat flux alone is not a representation, the time also comes into play. Unfortunately, the terminology is such that critical heat flux is what is referred to by this situation. What actually this is, it is critical heat flux is that heat flux. If you want to define it nicely, critical heat flux may be defined as that heat flux at which there is a sudden degradation in the heat transfer coefficient that happens. So, Q double prime divided by delta T is equal to H. This is the definition of the heat transfer coefficient according to Newton's law of cooling. So, Q double prime by delta T, the heat transfer coefficient in saturated nucleate boiling is very good. At the point of this maximum heat flux or critical heat flux, in these two situations, what happens? Where if you are in this situation 1, let me call it situation 1, you have no more inventory left. Situation 1, when you reach point of CHF, liquid is absolutely not there, and therefore what you see is the heat does not have a sink to go, and therefore the wall temperature starts to rise. What you see as an observer is an increase in wall temperature. What is the cause for it? The decrease, sharp decrease in the heat transfer coefficient. H drops significantly because there is no sink to take away the heat, and therefore the manifestation, what is observed, what is seen by you, by the student, by you, is an increase in the wall temperature. Critical heat flux manifests itself as an increase in the wall temperature for heat flux controlled situations. So, I have kept the heat flux at some value and just allowed it to go on continuing. There would exist a situation where there would be no more liquid in contact with the heated surface. That situation would cause the wall temperature to rise suddenly, and what you see is a sharp excursion that is moving along the same Q to the right, or this could happen even at a slightly small increase in Q you do, and immediately you would go to this situation. The point being, sharp reduction in the heat transfer coefficient is manifesting itself as a CHF, or heat transfer coefficient reduction manifests itself as a increase in the wall temperature. This is what is CHF. The mechanism by which this so called CHF occurs in this case is what we call as dry out. It is a very important term. Dry out, the English term, something is there, now it is dry. What was there? Liquid was there. The liquid is no longer in contact with the heated surface. The heated surface is as if it is dry. That is why it is called as dry out. So, dry out is the mechanism by which this sudden increase in the wall temperature happens. This mechanism causes degradation of the heated surface. So, if you continue to heat the surface further, That is, you didn't realize that water is no longer there and you continue to heat the surface, the wall temperature will start to rise even further. So, what I would see is, I would go along this path, go to this point where the heat transfer coefficient suddenly drops, wall temperature rises, I continue heating. So, I increase the heat flux, wall temperature will rise even more. Remember, this is a log scale. So, this could be of the order of 5 to 10 degrees. This CHF point would suddenly take you to about 500-600 degrees increase in temperature, and this manifestation from saturated nucleate boiling, this is single phase natural convection, saturated nucleate boiling all the way to CHF and beyond will give rise to what is called as post critical heat flux regions. So, this is called post CHF heat transfer or film boiling heat transfer. We will come to that definition a little bit later. Okay. So, CHF is kind of a misnomer, but it has been conventionally used and we will not change the terminology that much, but you must understand that it has nothing to do with the heat flux per se, it represents the situation where the heat transfer coefficient suddenly degrades. Now, let us go to this case 2 where you have heater coil. This you would have seen in this immersion heater in your buckets at home when you have to get hot water for bath. So, those who did not have geysers in the olden days would have this immersion heater, and you would always be warned that make sure that the water level is high enough so that the entire heater is inside the water pool. Why? So, if I pass a current through this and heat is being generated and I continue to do this. So, if I continue to supply heat, the mechanism here, if I just expand this wire a little, this heater coil a little bit, this is the heater coil. So, what happens is your amount of heat flux when it is high enough, so that the rate of bubble nucleation growth and departure is so high, this rate is so high, that means it is so fast and rapid that fresh liquid is unable to come and occupy the locations or positions left by departing bubble. This is very important concept actually, and this you would see how important this is when we discuss the CHF business here. So, I have on a surface a bubble which is there, which is trying to leave. Yes, very good, this bubble has left. Fresh liquid is going to come and occupy the surface. Remember, I told you there are pits and cavities at which bubble is formed. So, once the bubble grows like this at a particular instant of time, and when certain forces conditions are satisfied, this bubble will basically leave the surface. Okay. The fresh liquid will come and occupy. Contact angle becomes important, surface tension forces, buoyancy force, pressure forces, all these things become important. We are not going into the details there. All we are saying is, if this is so fast, the rate of bubble growth and departure is so fast that one bubble, next bubble is all coming so rapidly, there does not exist enough time for the liquid to come, occupy, get heated and grow. Other way of looking at it is, the liquid surrounding is almost at Tsat, or at a temperature where it can right away form the bubble. So, when it comes into a region, remember, wall temperature is the highest, temperature decreases as I go along this way. So, a liquid here, when it comes into this portion, is coming into a high temperature environment. So, already this is near saturation. When it comes here, it is really ready to nucleate, and when it comes and fills the cavity, it does not require any additional time for it to nucleate, etc. So, the bubble growth is so rapid. When the bubble growth from all different cavities on the surface is so fast, what happens is, this is as if there is a film of vapor forming on the heated surface. Remember, this dosa example which we gave, the film is because of the water vapor cushion that is being formed between the heated surface and the liquid, cushion of water vapor which is there, or we are giving example with water, therefore water vapor, otherwise it could be any liquid and its corresponding vapor. This film of liquid, remember we had this pool where there is enough liquid still, but the pool is such, the heater is now covered with a cushion of water vapor. Even now for the same heat flux, so heat flux I did not change, rapid boiling has started. What is going to happen? This cushion, thermal conductivity of vapor is much lower compared to the thermal conductivity of liquid. Therefore, what is going to happen? Your resistance to heat transfer across the vapor film is going to be very high. R vapor is going to be much greater than R liquid, and therefore the film is going to act as an insulation to prevent further heat transfer. So, whatever heat is being supplied through this coil, through this electrical heater is not going to be removed because of this, and therefore, what you would see, same as here, decrease in the heat transfer coefficient, H drops, wall temperature increases. This is T wall minus T sat. T wall minus T sat increases because of the sudden drop in the wall heat transfer coefficient. T wall increases, the curve again will behave exactly the way we have shown. What is different between situations 1 and 2? Situation 1, there was no more liquid available for heat transfer, right? The sink was completely lost. Therefore, you went through what is called as a dry out phenomena. Situation 2, what is happening is very different from there. Liquid is there in this pool. This is your pool. The cushion of water vapor is there around the heated coil. This is your liquid, very much there. The cushion of water vapor is going to cover the liquid, prevent liquid from reaching the heated surface and take away the heat. This situation is very different there. What is the thermodynamic quality here in this case? All liquid is almost gone as vapor, quality is near 1, X is approximately or near 1, or you would say very high, greater than 0.95, something like that, just to give certain numbers. Whereas here I could be in a situation where I am at 20% quality, but the heat flux is so high. That is why when you are making this dosa, you don't keep the flame too high when you pour the batter on the pan, because when you heat the surface so rapidly, you are going to have a cushion of vapor, and therefore the dosa would not be able to be spread evenly on the pan. So, you keep it on low to medium flame, or if the pan has become very hot, you sprinkle cold water on it so that the temperature becomes lower. That cause for this kind of a degradation leads to the same effect, decrease in the heat transfer coefficient, manifesting itself as an increase in the wall temperature. Manifesting means what you see as an experimentalist, what the people see. So, wall temperature rises. Wall temperature rises, exactly the same thing, but the mechanism which causes it is called as DNB, or departure from nucleate boiling. Departure from nucleate boiling. This is very, very important, because this is what occurs at low quality, high heat flux situations. Dosa, that is the example you need to remember. Dry out, on the other hand, occur, I am going to write here so that we can compare this. Dry out, this was DNB, this is dry out. Second mechanism, this is the other one. This typically occurs at high quality and can occur at low to medium heat flux values. Low to medium heat flux values. So, low quality, high quality situation. Both these mechanisms, these are mechanisms of CHF. Mechanisms causing drop in heat transfer coefficient an increase in wall temperature in heat flux controlled cases. We happen to call this CHF, critical heat flux. Now I hope you can see that heat flux doesn't have, meaning it's not a constant number. So if I have water boiling at 1 atmospheric pressure, there is no particular value of CHF that you can talk about. CHF depends on the situations. Okay, so please note and make a note that CHF is not a number which is a constant which would be given at the back of the book or something like that. It is situation specific heat flux control situation. This is what, these are the two mechanisms, and these two mechanisms will occur even in wall temperature controlled case. Now, what is the nature of the boiling curve? Heat flux control situation, we would follow this curve, and we are going to see if I decrease the heat transfer, if I decrease the wall heat flux, if I start to reduce it, I will not retrace this curve, I will not retrace this, but I will come somewhere here and I would come and join this curve at this point. So, I would go this way, film boiling, vapor would be in contact with the heated surface, good heat transfer would be lost. Finally, when the temperature of the heated surface comes to a value which is called T min or minimum film boiling temperature or Leidenfrost point, Leidenfrost temperature, the liquid would be able to come in contact with the heated surface, and at that point of time the boiling curve would go this way and come back to the nucleate boiling curve on further reduction in heat flux. So, for heat flux controlled case, you would get something like this as the boiling curve. Okay. Now, what is the other curve that you see in the books? We will quickly go through that. The other curve that you see in the book is nothing but what you see for wall temperature control situation, wall temperature controlled case. So, when you control the wall temperature, T wall is controlled, QW is what you get. I can't control both, right. So, Q double prime is equal to H T wall minus T sat. This is sacred. This definition is sacred for us. This is being controlled. This is what we dependent variable, correct, and of course, H is equal to Q double prime by T wall minus T sat. This is also sacred. What are we doing here? We do the same experiment, thought experiment, with wall temperature being progressively increased. When you go to this kind of an experiment, it is a little bit difficult to control because you have to progressively increase the wall temperature. How is wall temperature controlled? Wall temperature is controlled by having condensation or boiling happening on the other side where you want the phenomena of nucleation to occur. For example, if I have to give heat for boiling to occur, the temperature of the surface should be greater than the saturation temperature, which means some liquid must be there on the other side supplying heat such that the temperature of the wall remains constant. Which process gives you constant temperature? Condensation or evaporation. So, you have a heat exchanger where some steam is being generated or some condensation is happening, the wall temperature is constant because of that situation, and that is being used to generate heat for this kind of a thought experiment. When we do this kind of an experiment, you would go through exactly the same pattern, which is the boiling curve. You would go through single phase natural convection, you would go through saturated partial nucleate boiling, saturated nucleate boiling, and what happens here is you go to a nice value of nucleate boiling heat transfer coefficient, and then when you slightly increase this wall temperature. So, all this while you were TW1, you got QW1, TW2, you got QW2, you went on like this. So, TWN, QWN, these were all nice nucleate boiling conditions. I will now go to a slightly higher value, TWN plus 1 greater than TWN. that small increase in the wall temperature, what will happen is suddenly whatever we said here will start to happen. You can suddenly start losing moisture, losing liquid from the heated surface because of the fact that that sudden jump in the heat transfer coefficient is sudden decrease in the heat transfer coefficient is going to be caused by rapid evaporation, rapid boiling away. Or if it is this kind of a situation, you would see sudden development of vapor cushion on the heated surface because you have got to a temperature where suddenly rapid nucleation is happening. So, whatever be the case, in this situation you would see a heat transfer coefficient drop and a T wall increase. But the thing here is, instead of going this way, the curve would do this. You would start showing this kind of a trend. By that I mean, small increase in the wall temperature, you would see a decrease in the wall heat flux. This decrease in the wall heat flux is not going to be as predominantly dominant or as that you can see in a heat flux control case. You would see sudden dry patches, sudden liquid. So, you would have alternate contact of the liquid with the heated surface and a dry patch, alternate contact and a dry patch. So, what you would see is a scatter in the experimental plot, and once the wall temperature becomes greater than this so called T min or lead-in frost temperature. So, you go on increasing this T wall. So, when you go to T wall minimum, which is this lead-in frost point temperature, this will be the last time where any liquid is able to come in contact with the heated surface, and after that you would go into this part of the boiling curve. This region where you had this alternate liquid and vapor contact is the transition boiling region, and that is why it is typically shown dashed. This transition boiling region is seen primarily in wall temperature controlled case. Transition boiling represents the situation where you have alternate random, there is no order in which it happens, randomness is very dominant, very chaotic. You have liquid in contact with the heated surface at sometimes vapor is in contact, and this process continues until you get to a situation where liquid can no longer come in contact with the heated surface. That occurs when wall temperature is beyond the or at the location T minimum or lead-in frost temperature. When you come to this situation, liquid cannot come in contact with the heated surface. Further increase in wall temperature will cause the boiling curve to take this form. We will see more of this and how the film boiling region is going to affect the heat transfer, etc., in the next module. Thank you.